Hello students. So in the previous video we discussed about Z transforms and the definition of Z transform, and we took some example on how to find the Z transform of the signal, discrete time signal x of n, and how to locate the region of convergence. Now to understand the region of convergence better, so we should go through the properties of region of convergence. Okay. So in this video we start with the properties of ROC, and it is very important to understand these properties of ROC. Because of this only we can locate the ROC for the given signal. Okay. Now this ROC has certain properties, so I will take one by one, and I will take some example and I'll show you how it will look like when you plot the ROC here. Now the first one says the ROC of x of z consists of ring in z plane about the origin. So that means if I explain that graphically, so this is the z plane and it will have a circle . Okay, so this is for the first property. It will have a circle of a radius. This radius will depend, it will be like r, so from here to here it is r, but this value it depends on the signal x of n. So that is the first property. So it will have a circle that is called as a ring in z plane about the origin. Second one, the ROC doesn't contain any poles. So this is very important thing. The ROC, even if you get the ROC, it will be so here. So this, consider this as a circle. Now if this region is our ROC, just for instance I am taking this example. So here the poles will not be in this region, so it won't be present in this ROC. Okay, it will be either in the circle at any point, like here, it may be at the origin, or it may be here some point. We don't know where it is, but the poles doesn't lie, they won't be present in the ROC. So this is the second property. Okay, poles are not present in ROC. Going to the third property, it says if x of n is finite, then the ROC is the entire z plane except at z is equal to 0 or z is equal to infinity. So what the meaning is, if you end up with a finite value for x of z, then the ROC will be entire z plane except at origin. So that means here it will be like this, entire z plane except at the origin or infinity. So depending on what kind of signal you get, if it is positive time sequence, then it won't be present at the origin, but it will be present in the entire z plane. This kind of example we took in the previous video. And for if it is a negative time sequence, then it will be present, that means it will be entire z plane except at infinity, because if you end up with a finite value. So that is the third property. Fourth one says if x of n is positive time sequence, then the ROC is outside the circle. Okay, now this one we also took an example in the previous video for positive time sequence and negative time sequence and both positive and negative time sequence. So we will have a circle or ring. Now if it is positive time sequence, then the ROC will be outside this circle, and this circle will be of some radius that will depend on the signal. It may be 1 by 2, 1 by 4, 3 by 4, anything. The ROC will be outside the circle. Okay, so this is the fourth property. Now fifth one says if x of n is negative time sequence, then ROC lies inside the circle. So fifth property, so we have a ring of radius r. So this r value depends on the signal that we have. Now this case, negative time sequence, the ROC will be inside the circle. Okay, I am mentioning that ROC outside the circle, and here ROC is inside the circle. Why? Because it is negative time sequence. Now this sixth one, it says if x of n is both positive and negative time sequence, then ROC is concentric. So concentric means, I think we have taken this example as well. I'm just rewriting this. So we will have both positive time sequence and negative time sequence. So for negative time sequence, the ROC will be inside the circle, and for positive time sequence, the ROC will be outside the circle. So we will have this kind of situation. We will have two rings, one for positive time sequence and another one for negative time sequence. Now in this case, the ROC will be inside here. So this region is ROC. So ROC is concentric. So this is the sixth property. Okay, so this is how you have to remember graphically whenever the property we are going to apply that. And last one, if z transform of x of n is rational, then its ROC is bounded by poles or extended to 0. That means if you have for a signal x of n, if the x of z ends up in a rational way, that is in the form of p by q. So p of z by q of z. If it ends up in this way, then it is bounded by poles as well as zeros, and or it may be extend to infinity. So that is what it say. Extend to infinity depends on the kind of signal we have and where the value of n is varying. And if it ends up rational way, then it is bounded by poles and zeros. So where the numerator will give you zeros and the denominator will give you poles. Okay, so that is the seventh property. Now this is about the property of ROC. So we have to remember the properties till the end of this Z transform, which is very important. So this is how you have to remember. I have explained this graphically how it will look like each property. Let's we'll take some examples on this, and let's see how the ROC is located. Okay, so we'll start with the example here. So first one, it says we have a problem. It says determine the Z transform and ROC. So we have to determine Z transform and ROC for following signals So we have some signals to deal with, and they have asked to sketch ROC and locate poles and zeros. So this is the problem, and the first one given is x of n is equal to delta n. Second one is x of n is equal to delta n minus k. Third one, x of n is equal to delta n plus k. So here they have given k value will be greater than 0, and here the k value will be less than 0. So this is the problem. Okay, so let's start with the first one given x of n is equal to delta n. So the solution for this is, we start with the definition. X of z is equal to summation n equals minus infinity to plus infinity x of n z to the power of minus n. Now n is equal to minus infinity to plus infinity, x of n is delta n z to the power of minus n. Okay. Now from the definition of delta n, that is impulse function, delta n is equal to 1 for n is equal to 0, and it is 0 for n not equal to 0. So that means it is present only for the value of n that is 0, which means only at the origin. So therefore our x of z is equal to delta 0, that is only at the origin, z to the power of 0. Z to the power of 0 is 1, and delta 0, at delta 0 what's the value of signal? It is 1 here. So that is x of z is equal to 1. Now if you go to the property, say the third one, it says if x of n is finite, then ROC is entire z plane except at z is equal to 0 and z is equal to infinity. Now this is a finite value, so therefore the ROC will be entire, not will be, ROC is entire z plane. Now how to locate this here? So this is the real and imaginary axis. This is origin. Now this is entire z plane, and since it is a finite duration signal, there is no poles and zeros. So this is the first part. Okay. Now coming to the second signal, we have x of n is equal to delta n minus k, where k is greater than 0. Now take this, x of z is equal to summation n is equal to minus infinity to plus infinity x of n z to the power of minus n. If you substitute that, delta n minus k z to the power of minus n. Now delta n minus k is 1 for n minus k is equal to 0, and it is 0 for n minus k not equal to 0. Now if you simplify this, you will get n is equal to k, and for this we will get n not equal to k. So the meaning is, when n is equal to k, delta n minus k will be 1. When n is not equal to k, delta n minus k is 0. So we have to consider the case where n is equal to k here. So therefore x of z is equal to delta, I am taking this condition, n is equal to k, so k minus k z to the power of minus k. So that gives you delta 0 z to the power of minus k. So value of delta 0 is 1 into z to the power of minus k. or you can write this as 1 divided by z to the power of k. Now this is my x of z. Now the z transform, it is ended in terms of rational form, that is, it is in the form of rational. Now what does it mean? You have to look to the seventh property. It says if z transform of x of n is rational, then its ROC is bounded by poles or it may extend to 0. So that means we have if you take this one, we have poles in the region ROC, okay, and so not in ROC. If you equate z power k is equal to 0, that means at origin we have k number of poles at origin as k takes positive values. It may be any number, it may be 2, 3, 4, etc., any value it takes. Now coming to this ROC, ROC is entire z plane and it also includes k number of poles. So that is the seventh property we have here. It is bounded by poles. So first thing is it is entire z plane ROC. So just shade it like this, and here at the origin we have poles, and I will write this in different color, it will be easier to locate here. Now how many poles here? K number of poles. Where? At origin. So here it is. So this is what the seventh property says. We have ROC, but it is bounded by poles where the pole is near the origin, k number of poles. So moving to the last one, C, given x of n is equal to delta n plus k, where k is less than 0. X of z is equal to so this is the definition. Now if you substitute that, delta n plus k z to the power of minus n. Now it says delta n plus k is equal to 1 for n plus k equal to 0, and it is equal to 0 for n plus k not equal to 0. So if you simplify that, for n is equal to minus k, delta n minus k is 1, and when n is not equal to minus k, delta n plus k is 0. So based on this, we can write x of z is equal to delta. So we are considering only the condition where delta n plus k is present. So it is present where? When n is equal to minus k. So delta minus k plus k z to the power of minus n is there. So if you substitute minus k in place of n, that will become plus k. That becomes delta 0 z to the power of k, or you can write like minus of minus k here. It will be much clearer. So delta 0 value is 1 into z to the power of k. So the answer is z to the power of k here. Now the ROC, you might be wondering what is this z to the power of k. Here also we consider this because we have 1 into z to the power of k. So this is a finite value. So we consider that the ROC is entire z plane. ROC is entire z plane. Okay. And what about poles? We don't have poles, but we have the z power k can be written as z power k by 1. So that means z power k is equal to 0, means we have k number of zeros at origin. How means we can express this as z to the power of k by 1. So this gives you zeros and this gives you poles. So we don't have any zeta, means no poles there. In the numerator we have z to the power of k equating to 0 will give you the location of zeros, which is origin. Now ROC is entire z plane. Now if you plot this, so it will be entire z plane, and here we have zeros. How many zeros? We have k number of zeros at origin. So everything will be based on the property of ROC. You can see in each problem one of the property will be present. Now if you look at the previous video, uh, we have taken some examples. That means we have taken a positive time sequence, negative time sequence, and a sequence which is having both positive and negative time sequence. So if you observe this, the property 5, property 6 and property 7. So 5, 6 and 7 are evident in those examples. So for in positive time sequence, the Z transform is outside the circle. In negative time sequence, the Z that is the ROC is outside the circle. In negative time sequence, ROC is inside the circle, and in both the positive and negative time sequence, the ROC is concentric. And you can also observe in the same example, in the concentric one, uh, the poles and zeros, they are not present in the ROC. They might be near, it might be in the origin, or it might be on the circle, the ring. Okay, so not in the place of ROC. So that is very important. So this concludes the second property, and the first property says it consists of a ring. Definitely, when depending on your x of n signal, unless if it is a finite value, uh, you will get a, if it is in the form of p by q form, you will get a ring of a certain radius, and also the location of poles and zeros. But if it is just only a finite value like 1, 1 by 2, 3 by 4, 2, 3, etc., then the ROC is present for entire Z plane. So that is that is the example we took in the previous video. This example we are also taken in the previous video. Now I will go to one more example based on this, and let's see how we are going to find the ROC. And so in this one, the problem is given: find the Z transform of x of n is equal to 1 by 2 to the power of n u of n minus 2, and locate poles and zeros, locate poles and zeros and ROC. So this is the problem. So we'll start solving this. So x of z is equal to n equals minus infinity to plus infinity x of n z to the power of minus n. Now if you substitute that value given 1 by 2 to the power of n into u of n minus 2 z to the power of minus n. So, this u of n minus 2 is equal to 1 for n minus 2 greater than or equal to 0, and it is equal to 0 for n minus 2 less than 0. So, this gives the limit as for n greater than or equal to 2, and this gives n less than 2. So, that means for values of n which are greater than 2, u of n minus 2 is 1, and for values of n which are less than 2, u of n minus 2 is 0. So, based on this, our limit now changes from n is equal to 2 to infinity. Instead of minus infinity to plus infinity, it is present for value which are greater than or equal to 2, and x of n is 1 by 2 to the power of n z to the power of minus n. Now, if you combine this, we get 1 by 2 z inverse to the power of n. So, I will call this as 1. Now, this term should converge the ROC. This term will give you the ROC. From the geometric series, we have for n is equal to 0 to infinity a to the power of n, we can write it as a square divided by 1 minus a, where a is less than 1. This can also we can take this for ROC, because this the term is present here, or we can just take the term which you are applied before the geometric series. So, this should converge. This term what I have written here, this term should converge. Okay. Now, based on that, we can write in place of a we have 1 by 2 z inverse. So, I can write it like this: 1 by 2 z inverse whole square divided by 1 minus 1 by 2 z inverse. Now, if you simplify this, you will get, I will take this z below, and if you take the square, 1 by 4 z square divided by 1 minus, I will leave this 1 by 2 and I will take this z 1 by 2 into 1 by z. So, if you take this, you will get z minus 1 by 2 whole divided by z, and in the numerator 1 by 4 z square. So, if you simplify this, 1 by 4 z square into z divided by z minus 1 by 2, these two get cancelled. So, we'll remain with 1 by 4z divided by z minus 1 by 2, or you can write it like 1 by 4z into z minus 1 by 2, because we have to locate poles and zeros. Okay. So, this is x of z. Now, to the ROC, x of z will converge if, when it is going to converge, if this term is less than 1, mod of that term. If 1 by 2 z inverse is less than 1. So, if you cross multiply this, you will get 1 by 2 here less than mod z, or you can write it as z greater than 1 by 2. So, the ROC is located, z is greater than 1 by 2. Now, this value is what is nothing but the radius of the circle, and to locate poles and zeros, we have x of z is equal to 1 divided by 4z into z minus 1 by 2. So, we have numerator, we do not have any z term. So there is no zeros. So coming to poles, 4z is equal to 0 and z minus 1 by 2 is equal to 0. So this gives as z is equal to 0 and this is equal to z, z is equal to 1 by 2. So we have two poles at z is equal to 0 and z is equal to 1 by 2. Okay, and the ROC says is present greater than 1 by 2 means we have a circle of radius 1 by 2 and the ROC is greater than that. And if you can see this, the given signal is a positive time sequence signal because 1 by 2 n of n minus 2 which is present only for positive values of n. You can see 2 to infinity. That's why. Now if you go for plotting the signal, so first thing is we have a circle of radius 1 by 2. Now z is greater than 1 by 2 means the ROC will be an outside this circle, and I also shown that it is a positive time sequence. So therefore the ROC will be outside the circle. And coming to poles, we have two poles. One is at z is equal to 0 and another one is at z is equal to 1 by 2. So you might be wondering why I am not placing here somewhere here, because you can see z is equal to r into e power j omega, where r will give you the radius, okay, and this omega is the angle of z. So in the coming, the angle is not mentioned here. If there is no angle means we have to locate in the axis, that is 0 axis. It is at present at 0 degree. So that's why we are locating pole here on this axis and exactly at z is equal to 1 by 2 where the ring is there. Okay. So one is at the origin and another one is at the value z is equal to 1 by 2. So this is the point where z is equal to 1 by 2 pole is present. Okay. So this is the reason why if there is an angle present, we take that example also. If there is an angle present, then we can locate somewhere here depending on the angle, like if it is 60 degree or 45 degree, based on that we will locate the pole here, 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 anywhere. So depending on the angle we can locate that. If there is no angle, we have to locate the pole exactly on this 0 degree axis. Okay, so that's about the poles and zeros. And in the last video I gave some examples to solve, and I'm giving the solution for this. The first problem for x of n is equal to 1 plus n into u of n. For this, the solution, you'll get x of z as 1 divided by 1 minus z inverse whole square. I can further simplify this, and the ROC for this will be z greater than 1. So this is the first problem. And the second problem I give you like this: x of n is equal to a to the power of n plus a to the power of minus n into u of n. For this problem, you will get x of z as 2 minus a inverse plus a to z inverse divided by 1 minus a z inverse and 1 minus a inverse z inverse. So this is what you are going to get. and for this one the ROC will be 2 times. One will be Z greater than A and Z greater than A inverse or 1 by A. So these are the two conditions. So if this is the case, we take ROC as each one is having the maximum value, maximum of A and 1 by A. If you are end up with like this, if it is some value like integer value, if A is like 1, 2, 3 like integer value, then it will be easy. Which one is greater, that we are going to consider. If you have if you end up with this and we don't have the value of A, so we will consider that whichever having the maximum value of A, that will be considered. Say for example, both are positive time sequence, so you will have two rings. One will be having the radius of this 1 by A, another one will be having the radius of A. But depending, if A is greater than this 1 by A, then obviously the circle, this ROC will be outside the second ring, not concentric, outside the second ring, because these two are not positive negative time sequence. Both we got this for a positive time sequence only. We don't have positive and negative time sequence in the same signal. That is the reason. Okay. So hope you have got this answer. Just verify your answer with this one. And if you have any queries, do reply to the video, or you can comment on this video as well. Thank you for your time.